Hi, I'm Sarah, and this is a very condensed version of everything else that goes into Linsig. Okay, your professors have probably told you this by now, but all of Linsig can be summed up in four different equations, and those are the ones that we're going to be going over now. The first one is the system response to the unit impulse. So it gives you the unit step. Then the next one that we talk about is the convolution. And essentially, if you haven't covered this in class yet, a convolution is when you're moving one function. So you're looking at this one right here along another one. So this little guy is just doing this. And these can often get simplified. If you take a convolution and it looks scary and it has this fancy star icon, whatever we're doing here, and we throw it into an integral and then change the variables for the other function, it's actually just a multiplication. So it makes it a little bit easier. And then you can also convert it to the frequency domain and it'll also be a multiplication there, which is very nice. And you can also, if you have the convolution version written out here in signals and systems standard form, then you can do a change of variable on the h of t minus tau to get your h of t for the system, which is also super convenient. There's another nifty property that if you're convolving a function, so if you have x of t, for example, and you're convolving it with the delta function, so of x of, let's say, t minus 2, then you're actually just going to get a shifted version of your x of t. So the result of that is just going to be x of t minus 2. I'd recommend doing practice problems from old exams too, to see what variations of this problem they could give you. Sometimes there are extra variables, sometimes there are extra functions, but you're always shifting the entire equation by whatever that shift in the delta function is. Next to the eigenfunction property, where if you have a complex exponent like this, that you can get into this form where there's an I2 pi j of t, you can plug it into the system, and this is what your y ends up looking like. So that's the eigenfunction. And then the final thing we're going to look at is the Fourier transform. You're essentially taking a function from the time domain to the frequency domain. And again, your instructors should explain this pretty well during class, but it's just a different way of looking at a function by seeing how often it repeats itself. These are the relevant formulas, including the system transfer, which is a really good way. If you have the y of f, but not h of f, or not the x of f, you can convert among those pretty easily with just basic multiplication and division. Before your exam, I'd highly recommend looking up a Fourier transform table. The textbook has a pretty good one too, but there's one online by, I want to say it's ETH Zurich that put it out, that covers everything that you could imagine. It's in pretty good detail too. So with these four formulae, the tables, and then the lessons that you have learned earlier in the class and in your other classes too, with the basic algebra that you need, the calculus that you need, you should be pretty well set. But as always, if you have questions, please feel free to reach out.